the scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown. Nothing's really certain about what's going to happen.
It's a monster. It's unforgiving. It's relentless. It's spinning around so fast, its gravity is like a giant slingshot, slinging rocks, dust, electrons, whole comets. Anything that gets close to it becomes its weapon. Just so happens, deep inside this body are the secrets we're after. Secrets about our early solar system.
It's the biggest and baddest planet in the solar system, and it's got the biggest and baddest radiation and the biggest and baddest magnetic field.
The background radiation that we're exposed to on Earth is about a third of a rad. What we expect to see at Jupiter is about 20 million rad. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
So the real trick is, we gotta go in close, get the data, and get out. And the first time we go in, that's the most dangerous.
Magnetic fields have been a curiosity for thousands of years. And so, of course, we know now that magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Even though we can map the Earth's magnetic field with extraordinary accuracy with satellites in orbit about the Earth, the one thing we can't do is see clearly through all the crustal magnetization that is right beneath our feet. Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it. Juno's the fastest spacecraft ever to venture into the outer solar system. It's the first to orbit pole to pole about Jupiter, and it's the most heavily shielded spacecraft that we've ever launched. The mission is designed to basically wrap Jupiter in a dense net of observations, completely covering the sphere. So to do that, we need a polar orbit, one that passes over the North Pole, along a line of longitude, and over the South Pole. And we do this over the 37 orbits of the nominal mission, and by the time we're done, we've got orbits separated in longitude by about every 12 degrees. So we completely cover the sphere.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
Our roll program is in progress. Vehicle body rates look good. Booster PU has gone to fixed angle, surely will confirm. SRB chamber pressures have plateaued, I'm rolling off, signatures look good. RD-180 operation looks excellent at this point in the flight. Mach 1. SRB chambers continue to roll off.
The WAVES instrument is basically a radio. It tunes to frequencies all the way from 50 hertz, which is near the bottom of the audio frequency range, up to above 40 megahertz, which is above the limit of the radio emissions that Jupiter generates. The WAVES instrument has two sensors. One is designed to measure the electric field component of these waves, and it looks like a pair of rabbit ear antennas that you might have had on a TV when you were a kid, except these are about 10 feet long. The other sensor is a much smaller device. It's about 10 inches long, and it's basically a coil of wire. It has about 10,000 turns on it, and it's designed to measure the magnetic fluctuations of waves. So these two sensors are used by the receivers to study the various phenomenon, particularly in Jupiter's polar magnetosphere. For example, the maximum frequency of the radio emissions that we detect told us what the magnetic field strength was in the magnetosphere of Jupiter, long before any spacecraft arrived. Juno was designed to actually go to another planet and make the first measurements of an extraterrestrial auroral region in great detail. So I think we learn about ourselves by studying other environments in the universe.